Now the last video went through the Nyquist criteria. Now we're going to take a look at this specific example and walk through it quite slowly in order to try to start to make all of the connections between our different diagrams that we use to analyze closed loop stability. So we're going to try to connect ideas from the root locus, ideas from the Bode plot, and ideas from the Nyquist plots. So we're taking a look at an open loop plant that has two poles at -1. So in this case, all the open loop poles are stable. And we're going to use proportional feedback here in order to wrap this in unit feedback. And now what we're going to do is we're going to take a look at all these different diagrams. And so it would be useful if you're not familiar or not feeling comfortable with some of these tools. It would be good to go ahead and sketch the root locus and to kind of think through the Bode plot sketching the way that we've done it in the past. And what we're going to do now is we're going to motivate these in a slightly different way. So let's start at the root locus. So here you've got two poles at -1. And so what we're going to do is we're going to try to plot kind of the basic ideas of the Bode plot and the Nyquist plots from this root locus to understand another way to interpret these and another way to think about them. And so keep in mind that all of the Bode plot and the Nyquist plot use frequency domain information, which means we're going to be restricting ourselves to looking along the imaginary axis. So only the values of S that look like I omega. So those are only points along the imaginary axis. And so we're going to pick out a couple key points to help motivate how we draw these out. And so these A, B, C, D points, these are going to be consistent throughout. And so I'm going to show you how you can derive these. So one way of understanding the Bode plot is that this is the magnitude of G evaluated at I omega, and this is the phase evaluated at I omega. And so when we start from the poles, the magnitude is the distance from those poles to a specific point. And so if we're going to look at the point that is at omega is equal to 0, then the magnitude from each of these poles is going to be the distance from S is equal to -1 to S is equal to 0. And that magnitude, this distance right here, is just 1. And so we have two of these poles, so the magnitudes multiply, which gives us 1 times 1, which means that the overall magnitude of G of I omega is going to be 1. And so that's what we're plotting here. The point A is magnitude 1. And it's useful to note, though, that this horizontal axis is on a log scale. So we go 100, 10, 1, 0.1. So actually right here, this value is 0.01. And so the Bode plot never actually contains the value at omega is equal to 0. This is kind of a limiting behavior. And so you never actually end up plotting omega is equal to 0, but we can kind of think about this as being somewhat small enough that if I'm going to plot this magnitude, it's going to be something close to that. So this is close enough to 0 that this magnitude should be pretty close. So now if we look at the angle that these poles make to point at this point along the imaginary axis, S is equal to 0i, this angle is an angle of 0. And in this case, the phases add, and so the cumulative angle from the poles is 0 plus 0, because both of them are at the same spot. And so since those are in the denominator, the poles are in the denominator of the transfer function, that would be essentially still 0 because it's in the denominator, but the negative of the 0 is still 0. And so that's why point A has a phase of 0. So now if we move along, you can imagine that as we move along, point B is located somewhere around here, and that indicates an angle that's a little bit bigger than 0. And then we keep moving along, and we're going to get to the point where now we're at the point C, which is at S is equal to 1i. And so that corresponds to the frequency of 1. And so what we observe is that this now has a horizontal distance of 1 and a vertical distance of 1. And that means that this angle right here is a 45-degree angle. And so now a 45 degree twice, so we have two poles, so 45 degrees plus 45 degrees is 90 degrees. And that's going to be, again, the poles are in the denominator, and so that exponential receives a negative sign when you take it to the numerator. And so that means that you now have a negative 90 degrees for your phase. And so that's why the point C has a negative 90 in its phase. This distance, because this is an isosceles triangle, we know that this has distance 1, horizontal distance 1, and vertical distance 1. Then this distance is square root of 2. And so that means that now the magnitude looks like square root of 2 times square root of 2. And again, that magnitude is in the denominator. And so that's going to give us 1 over the square root of 2, 1 over the square root of 2, which is going to give us 0.5. And so the value here, it's hard to see on this plot, but the value of that magnitude is 0.5 in this case. So keep in mind when I'm talking about these magnitudes and distances, we're talking about that we're going to think about the transfer function as being something like a magnitude z1 times e to the phi I phi 1 and z2 times e to the I phi 2. And so these are our phases and these are our magnitudes. And so that's why when we write this into equivalent form, this is going to be 1 over z1 z2 times e to the I, and then it's going to be minus phi 1 minus phi 2. So this is why the phases get a minus sign and why they also essentially add. And this is why the magnitudes are reciprocaled in this case, and they multiply. All right, so now as we keep increasing the frequency, that means that we keep moving along this axis. And as that gets larger and larger, the bigger and bigger that gets, when that point goes all the way up here, you can imagine keep going further and further. This angle that points up all the way up to there, this angle here gets closer and closer to 90 degrees. And so that means as omega goes off to infinity, this angle is going to get closer and closer to 180 degrees because each of the poles contributes 90. And so that's what you see. You see we're approaching minus 180 as you get larger and larger frequency value. And so then this distance here, the distance away, gets bigger and bigger. And so that means 1 over the multiplication of these bigger, really large numbers creates a magnitude that's essentially going down and getting smaller and smaller. And so this is a way to understand from the root locus how to go and sketch out the Bode plot from the angles from the poles and zeros. In this case, we have no zeros, but from the poles, 2 points along the imaginary axis. So again, we've seen one way of sketching out the Bode plots, and now this is another way to think about the Bode plots. When we take that into the Nyquist plot, what we observe is that we can also sketch this. And where this is magnitude and phase, the Nyquist plot is now the real part and the imaginary part. And so this is saying the real part of g of s, and this is saying the imaginary part of g of s. And so a specific point on this blue curve is indicating this is exactly just what this is saying. This is g at I omega. And this is essentially going to be, the point is going to be the real part of g of I omega as the x, as the horizontal piece, and the vertical piece is going to be the imaginary part of g of I omega. So those x and y coordinates there, the horizontal and vertical components, are the real and imaginary points of g of I omega when it's evaluated along the imaginary axis, because again, this is frequency domain information. So again, if we come back here, we know that the magnitude is 1 and the angle is 0, which means that everything is real. Everything is in the real axis. So we have a real part. So again, point A here, the real part is 1 and the imaginary part is 0. And so that's why point A is right here. We have a real distance of 1 and it's on this horizontal axis because there is no imaginary part. And so that's omega is equal to 0. As we increase omega along the positive imaginary axis, we get the point C, and that was a point where the magnitude, we said here the magnitude was going to be 1/2, because that was 1 over square root 2 times 1 over square root 2. And so the magnitude is 1/2 and the angle is minus 90. And so that's here you can see the angle being minus 90 takes us to the vertical axis now. And we put a point down here at when the magnitude, so this distance here is 1/2. So that's exactly where point C is, which is omega is equal to 1. And as we now increase that further, larger and larger, the angle is going to slowly approach 180. And so as we do that, we're seeing this angle is getting closer and closer to 180. But as it gets closer and closer to 180, we know that the magnitude is decreasing. And so the magnitude is getting smaller and smaller. So in the limit, as it approaches minus 180, you'd think that we'd be pointing along this direction, which we are, but it's happening at a point that's very, very close to the origin. So it's getting closer and closer. And so this curve right here is the positive axis of the positive area, corresponds to the positive imaginary axis here. Notice that the Bode plot plots only positive imaginary axis, so just positive frequency values. The Nyquist plot is always going to be symmetric because it's also plotting the negative values as well. So this is along negative values. So as it goes from negative infinity, it comes back around until it gets up to 0. And so we're going to see some effects of what happens as you go through 0, essentially, because the Nyquist is going to plot everything along this whole imaginary axis. All right, so that shows how you go and connect root locus to the Bode plot and the Nyquist plot. And then finally, we can go ahead and use the Nyquist plot criterion in order to determine stability. So in this case, the question is, does this encircle minus 1? And so this is for the nominal gain value, which we'll say is k is equal to 1. And so at this point, minus 1 is somewhere over here. So you'd have to extend this out. This is minus 1. And so this point is not encircled at all by this heart shape. And so in this case, the closed loop system is going to be stable because all the open loop poles are stable. So we need to make sure there's 0 and counterclockwise encirclements of the point minus 1. And indeed there are. And so for this value of k, there are no encirclements. And so now I want you to just kind of think through this little mini activity. And on top of this, draw what you think this shape should look like when k is equal to 2. So think about what that means here for this magnitude plot. We know the phase doesn't change, but the magnitude gets shifted up by a little bit. And so keep in mind that where this is a point on the imaginary axis, this is the real part and this is the imaginary part. This distance here is actually the magnitude. So this is g of I omega, the magnitude, which is plotted on the Bode plot. And then this angle right here is the angle of g of I omega. So that's the direct connection between the Bode plot and the Nyquist plot. So now that we're going to multiply and increase the gain to k is equal to 2, imagine what it means to inflate this Nyquist plot. So we're going to kind of do this visually, and that's going to be our visual test to see whether or not it's possible for this point minus 1 to be encircled by this shape that's in the Nyquist plot. So go ahead and try to think through how you might inflate that, and I'll show you my solution. All right, so now that you've thought through that, this is what it looks like. So again, this is the magnitude. And so if we were going to change and multiply by a value of k that's twice as much, we would expect that the both the x, so this is the x or the real part, and this is the imaginary part, and so both of those are going to double. So you're going to double that out, and so the corresponding point would be around right here, because again the phase doesn't change, and so twice that would get you out to here. So you're going to essentially expand this heart shape from the Nyquist plot by a factor of 2. But this, of course, depends on the initial value. And so everything's going to get pushed out. So that means that a point at 1 now becomes a point at 2. A point at 1/2 becomes a point at 1 now. But what's important is that a point at 0 does not get expanded outwards. And so I affectionately call this the butt crack of this heart shape. And so that butt crack does not move. And so you can see that it still tucks itself in here. And so for that reason, you can be extremely confident that this point -1, which is the critical point for evaluating Nyquist stability, is never going to be encircled. And so what we can say is that with 2 stable open loop poles and no unstable open loop poles, the Nyquist plot is never going to encircle -1. And that means it's going to be stable for all gain values. And so you can imagine that if you multiplied k by 1,000,000, you may have a much deeper butt crack here that essentially extends out, but that it will never actually include the point -1 because these are asymptotically approaching to 0 here. And so this is confirmed by looking at the root locus, which shows that we know that there's no value of k that's actually going to lead to unstable closed loop poles.